Oh, hi guys, Mr. Janowski here. Here is the third part of the slides for Chapter 9 about energy. In the first two parts, we learned pieces of the bigger idea. So in the first part, we learned work. In the second part, we learned different types of energy, kinetic energy, gravitational potential energy, and elastic potential energy. And then in this part, we're going to put those ideas all together into one much bigger idea. That bigger idea is called the law of conservation of energy. And in addition to that, you're all going to be able to see me struggle through using a Wacom tablet, which I just got for this. And I keep playing with it, and I keep not getting any better at it. So those of you who know how to use these, visual artists, and other people who are good at these, yeah, I envy you. Yeah, you're in for a treat. So let's get started with that. Oop. So real quickly to review, what is our formula for work? So try to think of the answer in your head. The formula is work, W is equal to FD cosine theta. Magnitude of force times magnitude of displacement times the cosine of the angle between them. What is our formula for KE, kinetic energy? That is 1 half mv squared. What is the formula for GPE, gravitational potential energy? GPE is equal to mgh. And the last one, this is the one people tend to struggle with the most. What is the formula for EPE, elastic potential energy? EPE is equal to 1 half kx squared. So K is the number for spring constant. That's the number that tells you how strong the spring is. So if it's a big, heavy spring, like you might see on the shocks of an old truck or something, that would have a very large value for K. If it's a very wimpy spring, like a slinky or something like that, that would have a very small value for K. And then X is the extension or compression of the spring you're dealing with. So how much is the spring either stretched or compressed? So all these formulas, very useful just to memorize them. They will always be on the footer when you need them, but these problems will go much better for you if you become fluent in them, meaning you have them just in your brain. You don't always need to check the footer to see what they are. So real quick, the work energy theorem. I'm going to show you the work energy theorem because as a physics teacher, I'm kind of obliged to show you the work energy theorem. However, it's not really the way we're going to be doing the problems. But if you go on and study physics in college, you'll see this idea and they will have expected me to have taught it to you. So I'm teaching it to you now. So what the work energy theorem says is sum of the work internal. Internal work is just a weird way of thinking about potential energy differently, basically is how it works out. But I don't want to go too much into that because that's not how we're going to do these problems. Plus, the sum of the external work is equal to the change in kinetic energy. So this is all perfectly true. I just don't think it's the best way to do the problems. The best way to do the problems is this way, with the law of conservation of energy. So this says sum sigma E initial plus sigma work external equals sigma E final. Energy is conserved. This is also called the first law of thermodynamics, the law of conservation of energy. Energy is neither created nor destroyed. Whatever amount of energy you start with, plus whatever amount of work from the outside gives you more energy or takes energy away from you, tells you how much energy you have to end up with. Because however much energy there was at this time in the universe, you have to have the same amount of energy at this time in the universe. So we can look at it here. And again, this is just what the three terms mean. If you add up all of the energy, so sigma, meaning sum, add up all of the energy you have at the beginning, and then you factor in any external work. Is anything from outside of your system giving you more energy or taking energy away? That tells you the total sum of energy you must have at the end. So again, however much energy you have on the left side, you have to have the same amount on the right side. That's all this law says. And we have an ugly slide coming up. So this ugly slide, I've just turned each of these three terms I've kind of just expanded them into what they actually mean. And then in the last step, I've turned each of those things that I just expanded into what they actually are too. So I expanded it and then expanded it again. But yeah, what this is saying is sigma E initial. So at the beginning of your problem, you might have energy in a few different forms. We're going to care about three different forms. Kinetic energy, your thing might have that. It might have GPE, and it might have EPE. And it might have none of those types, or it might have two, or it might have three. Or it might have other forms of energy like heat or chemical energy. Or if you remember from Albert Einstein, E equals mc squared, that is energy too. If you want to learn more about that, take physics 2. I'll teach you all about that next year. But anyhow, this first term becomes these three terms. This second term, sigma work external. You might have one thing giving you extra work or taking work away, and you might have another thing. And you might have another thing, and another thing, and another thing. There could be lots of different things adding or removing energy from your system, or there might be zero things doing that. So this term could be zero. It could be a million separate terms. And then on the right side of the equal sign, sigma E final. Again, you're going to have energy at the end, possibly, in these three different forms: kinetic, gravitational potential, or elastic potential energy. And then in the last step, I just expanded all of these guys into their formulas. So I like to say I turned the things into the things. That's what we did. So when you're doing these problems, you're going to want to ask yourself three different questions. The first question is it moving? If your thing is moving, it's going to have kinetic energy. So if V is not zero, it will have kinetic energy. Second question, is it at a height greater than zero? So you may have things changing heights in these problems. If it's at the lowest height and you're calling that one zero, then you don't have to worry about GPE, because if H is zero, then GPE is going to be zero. But if it's at a different height and you do have and H is not equal to zero, then you will have GPE. And finally, the last one, EPE. Is there a spring that is extended or compressed? You may have a problem that has no springs in it at all, in which case don't worry about EPE. And you may have a problem where you do have springs, but the springs are not extended or compressed. The spring is just sitting there. If our problems have a spring, it'll probably just be sitting there either at the beginning or at the end of the problem. It depends. But if it is extended or compressed, that means X won't equal zero. If X is not zero, then EPE won't be zero. If, however, X is zero, EPE will be zero. So I'm going to show you how to do these problems. Oh, I just realized I left a typo. You'll see. I'll show you how to do one of these problems using a nice little strategy. So here's me struggling how to use a Wacom tablet. So we're going to have a 2 kilogram textbook sliding across the floor, eventually coming to a stop. If its initial velocity, that shouldn't be has, it should be was, 1.80 meters per second, how much work does friction do on the book? So as usual, here's me struggling with the Wacom tablet. Let's go cadmium red. Nice color. As usual, start off with step Oop, I hit the button and the thing slid around. All right. Step what are we looking for? We're looking for how much work does friction do? So we're looking for W sub K, work of kinetic friction. So this is equal to question mark, and the units for this will be joules. Next, we want to make a sketch, which we'll use Van Dyke Brown for that. Why not? So yeah, all year long. It looks suspiciously like black to me. All year long, step 1 is make a sketch. This is a conservation law, so you actually want to make 2 sketches. You want to make an initial sketch. All right. Initial, I can spell. An initial sketch, and then we'll want to make a final sketch. So our initial sketch. There's me trying to draw a straight line. Sorry. And my computer is getting laggy. All right. We're just going to go with this one. No, we're not. That clearly looks like a hill. All right. Call that a straight line, meaning a level line. And I'm trying to draw and my computer is getting laggy. Okay. So there's a book. I'm not going to put any more detail on the book. So the book is moving. The book has a mass of 2 kilograms. It's got an initial velocity of 1.80 meters per second. And what height is it at? This thing's not going to change heights throughout this problem. So we're going to say it's at a height of 0. So there's our initial sketch. Now we also need to make a final sketch. So when you're doing a conservation problem, there you should have an initial sketch that shows you what's happening at the beginning, and you should have a final sketch that shows you what's happening at the end. So final sketch. This is a really exciting picture. There's just a book sitting there. It is no longer moving. There's no speed lines. So what we're going to say is V final is 0 meters per second. And what height is it at? Well, it hasn't changed heights. So H final, 0 meters. Now on, Now on to step 2, French ultramarine. Fancy. Step 2 is going to be write the law of conservation of energy. So the law of conservation of energy says sigma E initial, sum of your initial energy, plus sigma work external, the sum of your external work, is equal to sigma E final, the sum of your final work. So now we go through this term by term. We look at our pictures and we decide what kinds of energy we have by asking 3 questions. So look at the initial sketch. First question, is it moving? Yes, in the initial sketch it is moving. So we do have kinetic energy. So we are going to have a term for KE initial. Second question, is it at a height greater than 0? No. We're calling this height 0, so we're not at a height greater than that, which means there's no GPE to worry about. And third question, is there a spring that is extended or compressed? There's not a spring at all, so there's no EPE. We don't have to worry about that. Now your next term, sigma work external. Is there anything from the outside that's giving us more energy or taking energy away? In fact, there is. There's friction. That's what we're looking for in this problem. So that means we're going to have a term for work due to kinetic friction, and then equals. Look at your final sketch and ask yourself 3 questions. First question, is it moving? No speed lines, V final is 0, it's not moving. So there's no kinetic energy. Is it at a height greater than 0? Nope, the height is still 0, so there's no GPE to worry about. And third question, is there a spring that is extended or compressed? There isn't a spring, so there's no EPE final, which means the entire right side is just equal to 0. So now on to step 3, which is math. So if this were a momentum problem, the first part of math would be take the hats off and put in the signs, but these things are all scalars. There's no hats. We don't have to worry about that. So we're just going to turn the things into the things. So kinetic energy. Remember your formula for KE is 1/2 mv, I'm going to call it V initial squared, plus, I could turn this into FD cosine theta, but the thing we're looking for is actually already, let me just circle it. It's this guy here. So yeah, I don't even need to change that. I'm going to just keep calling that W sub k, and this is equal to 0. So you've got to do a little bit of algebra to get that thing by itself, and what you'll end up with is W sub k is equal to minus 1/2 m V initial squared. And now we've taken it as far as we can with the letters. We got to go to the numbers. So minus 1/2. Sorry, my thing's getting laggy. There's my 2. Minus 1/2. Our mass is 2.00 kilograms. And our velocity initial was 1.80 meters per second. And this thing gets squared. So if you get out your calculator, plug those numbers in, minus 1/2 times 2 times 1.8, you hit the x squared button, you're going to get, here we are, minus 3.24, and the units for this are joules. we've just figured out, a work, so its unit should be joules. So put a box around it, and then do step, think about your answer. We solved for the right thing. We did solve for work done by friction. Remember, that's what we were looking for up here in step, we gave it the right units. It's units of joules. It's negative. Does that make sense? It does make sense. Friction will do negative work. Friction is only ever going to take energy away. So we like this answer. Give it a check. So now, I don't know why scrolling on this is so difficult. Worked perfectly. So now another problem. So in this problem, what do we have? We've got a spring with spring constant of 325 newtons per meter. It is compressed downwards by 0.100 meters, and a 0.145 kilogram baseball is placed on top. How high will the ball go if the spring is released? So we will start off with step, What are we looking for? So we're looking for how high will the ball go if the spring is released? So really what we want is the height final at the end of this problem. So that will be question mark. And the units for this, it's a height. It's going to be units of meters. So on to step 1. Mars black. Wonderful. So step 1, you've got to make your sketches. This time I'll spell it right. Your initial sketch. So what do we have? We've got a floor. We've got a spring. On top of this spring, there's a little platform. Yep, we have a baseball. So there's your baseball. The spring is compressed. So let me draw on this little dashed line all the way across. The spring is compressed. The spring wants to be at that initial height, but we've compressed it a little bit. So that means x initial is equal to 0.100 meters. And what else do we know? The mass of the ball, 0.145 kilograms. Let's see. The velocity of the ball initially is 0. There's no speed lines. The ball's not moving. And the height of the ball initially, what height is it at? H initial is 0 meters. So now on to the final sketch. So it's not that difficult to use this until the computer starts getting laggy and I start writing things and then they don't show up right away. Okay, so final sketch. Our spring is released. So this dotted line here represented the height that the spring just wanted to be at. That's what's called its equilibrium point. So now the ball is up in the air. And things to consider. Let's see. The mass, that hasn't changed. I'm not rewriting that. X final. The spring is no longer compressed. There is still a spring, but it's not compressed. So X final, the compression of the spring is 0. What else? V final. So is the ball moving? Think about this carefully. The ball obviously moved from here up to here, but it's now at its highest point. So think back to kinematics. When the thing is, if you throw something up in the air, when it's at its highest point, that's when it's run out of vertical velocity. So it was just moving up. It used to have speed lines behind it. And it's about to start moving down, so there will be speed lines above it. But at this exact instant, it's not moving. It's just for an instant, it's at rest. So V final is 0 meters per second. And the last thing we want to know is H final. What height is this at? We don't know this. This is actually what we're looking for in this problem. So H final is question mark meters. So let me go back and grab a blue. I keep trying to use this thing like a trackpad, and it just ain't a trackpad. Red, blue. Okay. Some would call that purple. That doesn't look like purple, but that's what we're going with. So yeah, try to remember what would be the second step in a problem like this. It would be to write the law of conservation of momentum, or conservation of energy. Sigma E initial plus sigma work external equals sigma E final. So go back, look at your sketches, and then figure out what types of energy you have. So let's look at our initial sketch and ask our 3 questions. 1, is it moving? Nope, V initial is 0, there's no speed lines, it's not moving, so there's no initial kinetic energy. Second question, is it at a height greater than 0? It is not. It's at the lowest height it's going to be at, and we're calling that one 0. So there's no GPE initial. And third question, is there a spring that is extended or compressed? There is. There is a spring. It is compressed, which means we do have to worry about EPE initial. So this term here, sigma E initial, becomes this, EPE initial, plus sigma work external. There's no friction. There's no air resistance that we care about. There's nothing else giving us or taking away energy. So that is just 0. So I wish I had a little more room. Boop. That goes to 0. We're not worried about that term. And then finally, sigma E final. Ask 3 questions. So look at your final sketch. Is it moving? Nope. V final is equal to 0. Second question, is it at a height greater than 0? Yes, it is. We don't know the height, but it is clearly at a height greater than 0, which means we are going to have GPE final. And then the last question, is there a spring that is extended or compressed? Well, there's definitely a spring, but all the energy has left the spring. The spring is, its compression is 0, X final is 0, which means there's no EPE final. So we don't have to worry about any of that. So let's go with deep chrome green for doing step 3. So if you'll remember, step 3 is math. So turn the things into the things. EPE initial. So think about your formula for EPE. That is 1/2 kx initial squared. And this is equal to GPE final. So try to remember your formula for GPE. mg h final. So now I have this little equation, and we've got to figure out which of these things are we actually looking for. So check your step, We're looking for h final, which means I've got to do the algebra that gets this guy by itself on one side. So what's that algebra going to look like? I'm just going to divide both sides by mg, and then I'm going to flip left and right to make this a little bit easier to write. And what that's going to give me is h final is equal to 1/2 kx initial squared divided by mg. And in the past, people have asked, is the half on the top or is it on the side? It doesn't really matter. It works out the same. So now we're going to put in our numbers. And what are we going to have? H final is equal to 1/2 K. K is 325 newtons per meter times X initial. So X initial is 0.100 meters, and this gets squared. And then we've got to divide it by the mass. So the mass is, computer getting laggy. That doesn't do. Why is it getting laggy right when I'm trying to draw a 0? There we go. The mass, 0.145 kilograms times G. G is, use the positive number, 9.8 meters per second squared. So go to your calculator, do all this stuff. Do 1/2 or 0.5 times 325 times 0.100 x squared, then divide by 0.145 and divide by 9.8. If you do all that, you're going to end up with 1.14. Sorry, let me watch the screen as I'm writing, otherwise this looks crazy. If you do this, you end up with 1.14, and the units are meters. So make sure you get the order of operations right when you're doing this. Yeah, it's very easy to do the whole top part correctly and then divide by this. And then if you hit times 9.8, you're not putting the 9.8 in the denominator, you're putting it in the numerator. So figure out how to do that correctly on the calculator. But anyhow, yeah, I got this number and quick step, does this match my step, I solved for the right thing, H final. I gave it the right units, meters. And let's think of this number, 1.14 meters. So a little bit more than a meter stick. Does it make sense that a spring can pop a baseball up in the air 1.14 meters? Yeah, that seems logical. So we give it a check. So hopefully that makes sense. Now back to the slides. Nope, not that one. What's going on? Okay, here's the slides. Yeah, so in the slides, I'm just going to race through this. Yeah, there's all the work I just did. There's all the work I just did for the second problem. And quick review. So, what is the law of conservation of energy? This is also called the first law of thermodynamics. It says energy is neither created nor destroyed. And if you write it mathematically, it looks like this: sigma E initial plus sigma work external equals sigma E final. And quick, do you remember the formula for KE? KE is equal to 1 half mv squared. The formula for GPE: GPE is equal to mgh. And EPE: EPE is equal to 1 half kx squared. So when you're doing these conservation of energy problems, you have to ask yourself three questions. What is the question you ask to determine if it has kinetic energy? You want to ask, is it moving? For GPE, if you're trying to figure out if your thing has GPE, look at your sketch and ask yourself, is it at a height greater than 0? And finally, EPE, look at your sketch and ask, is there a spring that is extended or compressed? So that's the end of the slides. Hopefully this was helpful.